Hello everyone. We will start with the quantum chemistry and we will be covering the book Ira and Levine. So you don't have to. Okay. So in we have a famous scientist Isaac Newton who explained the laws of macroscopic objects, which are known as Newton's laws of motion. So laws of motion for macroscopic objects. Then, in the late 20th century, physicists found that the nature of microscopic particles, so the nature of microscopic particles, such as electrons, protons, etc., they don't obey these laws. So, using Newton's laws of motions, we can predict the nature of macroscopic objects, but for microscopic particles, um, these laws don't obey. In that case, so in that case, some other if the nature of the microscopic particles has to be explained by some other laws. So there comes the law of quantum mechanics or quantum mechanics help in predicting the nature of microscopic particles. So by understanding the quantum mechanics, we are able to describe the nature of microscopic particles. We will be able to predict the motion of these particles, and we will start by going in year in 1803. We have a scientist. So in 1803, we have a scientist called Thomas Young who conducted an experiment known as double slit experiment. So in this experiment, what happens is that um, we have a wall with two slits on it. Okay, and to observe the particles behavior, we have a photographic plate. So here we have a photographic plate. Okay, and at the center we have an electron gun. So naturally, if any particle is ejected or if the electron is ejected, so it can go through these two routes. Okay, and can be collected over here and here. So this experiment was conducted to observe the nature of the motion of electron. And naturally, uh, scientists can predict that the electron can go through either of these slits and get collected here. Okay, but instead of getting the uh, various electrons at these two spots, we have electrons uh, located at the center, the edges, and as soon as we are getting far from the edges, the intensity is low. So we are ejecting electrons continuously, and if 1 billion electrons or even more are getting ejected, then we find this kind of interference pattern. Okay, so this is ball with two slits, and we have an interference pattern over here. Okay, so mm, in this way, we expected that the particles would go in these two spots, but we got an interference pattern which explains that the electron, a single electron, does not have a fixed position. It can go in this whole region. Okay, this high spot, these high spots are known as crest, and these bottom spots are known as trough. So here the density of electrons are low, and here the density of electrons are maximum. Okay, so this explains that electron is not going through either one of the slits, it is going through both the slits. So the electron is acting as a wave nature, and it is interfering with itself. Okay, so we have two terminologies here. First is diffraction. It is the bending of the wave around an obstacle. Okay, and next is interference. So it is the combination of two waves of the same frequency. So it is a combination. It is either a sum or addition or a subtraction. Okay. Then in year 1864, we have James Clerk Maxwell, who gave the equations of electricity and magnetism. He gave four equations which unified the laws of electricity and magnetism. So through some experiments, he predicted that uh, the the electromagnetic waves are a combination of both the electric and magnetic component at 90 degree, and through this combination we explain that the electromagnetic wave travels through these experiments, he revealed that the electromagnetic wave travels with the speed of light. Okay, so the speed of light c is equals to 2.998 into 10 to the power 8 meter per second. So he concluded that light is an electromagnetic wave. Okay, and through this we get the electromagnetic spectrum, which consists of different electromagnetic waves in increasing order of frequency. Uh, these waves are radio waves, then microwaves, then IR, visible light, UV, X-rays, and then gamma rays. All of these waves travel with the speed of light. So if these waves travel with the speed of light, then they have energy E is equals to h nu. And here the frequency is equals to hc by lambda. Okay. So through these equations, we get that nu into lambda is equals to c. Okay. Then in year 1890, uh, we have some experiments conducted on the black body, and black body is any sort of an object um, that absorbs all light falling on it. You can assume it as a whole kind of thing. So if we shine light on it, it will just absorb it. Some experiments were conducted on the black body at different temperatures, and we found that when there were different kind of light, so here we have a black body, and when light is falling on it at different frequencies, at different intensities, and at different temperatures, we can get at particular frequency the variation of intensity with temperature. So when we talk about the intensity at increasing temperature, first of all, the sorry, uh, at increasing intensity at a particular temperature, we get the intensity with the frequency, and with increasing frequency, the intensity first increases and then up to a certain level, and then it decreases. So to explain this, we have Max Planck in 1900. He gave the equation which explains this phenomena, and the equation is intensity of light falling on a black body is equal to a nu to the power 3 e b nu by t minus 1. So he gave these equations where a and b are uh, these empirical constants. A and b are empirical constants. So through these black body experiments, uh, Planck assumed that atoms inside the black body behave like tiny oscillating electric charges and can only exist in discrete packets. So the atoms inside the black body, so they behave like oscillating electric charges and can only exist in discrete packets. If they only exist in discrete packets, so we have E is equals to h nu, and these packets sort of we can represent it with an constant n, where n is equals to 1, 2, 3, and so on. So these packets of energy, they are getting released when light shines on it. So these are getting absorbed by the black body. And when black body absorbs this kind of energy, the electrons or the electric charges inside the atoms, they oscillate. Okay, so we can say that the energy is quantized. So we have quantized energy. Okay, and we have the value of h, which was given by Planck as 6.626 into 10 to the power minus 34 joule into second. Okay, then Einstein came and explained the photoelectric effect in 1905 by Albert Einstein. He explained that when we have a shiny metal surface, so this is a metal, and when light shines on it with frequency mu, so when light have the packets, we can say that light has um, photons. So these photons are getting emitted and shine on the surface of metal. These lead to the ejection of electrons. Okay, and the metal has nucleus, and then there are these electrons. So these are negatively charged electrons. I'm just representing some of the electrons here. So there are these intermolecular forces, so attraction forces between the nucleus and electron, and repulsion force between electron and electron. So to overcome this kind of energy, when we have light shining on it, this help in the ejection of electron by nullifying these forces, and then the remaining energy is getting converted into the kinetic energy for the movement of electrons. Okay, so we have E is equals to h nu provided by light, which is equals to, so we have a function phi plus kinetic energy T. Okay, phi here is the work function, and T is the kinetic energy of electrons. Okay, so as the nu increases, the kinetic energy of electrons also increases, and intensity when the intensity of light increases, the number of electrons, the number of ejected electrons increase but their kinetic energy remains same because of the same frequency. So when we increase the light intensity, so it increases the number of ejected electrons, but their kinetic energy remains same. And by increasing the frequency, we are basically increasing the energy. So these leads to the increase in the kinetic energy. Okay. So when we have a proton and electron in an atom, so these are the shells. N is equals to 1, 2, 3 number of shells. And when we shine some kind of photons, so there is an activation of these electrons. These electrons can jump from one energy level to another. So the energy of upper electrons, if there is any transition, minus the energy of lower is equals to h nu. Okay. Okay. Then we have de Broglie's de Broglie's hypothesis states that it came in year 1923. So this suggested that uh, the motion of electrons might have a wave aspect. Okay, and we can have the lambda is equals to h by p, which is equals to h by mv. Okay, so he hypothesized that when we increase the wavelength of any wave, then its momentum decreases. Okay, and the wavelength is inversely proportional to p.